I'm recording right now. Okay. Today we're going to just review some not that difficult, simple examples of linear regression, logistic regression, and regularization. I made up some examples, and also there is one example here, which is mostly about how to use scikit-learn in linear regression. And I use the link here. The complete description of the example is there. You could reach there after this tutorial. Okay. About linear regression. You all know how it works. We're going to find a relationship between some independent variables and one dependent variable. Mostly in the regression, dependent variable is a continuous variable. If you would touch multinomial regression, I mean multi-class regression, or even logistic regression, the output, which is the label of the data instances, could be categorical or binary. So it's all discrete, but not for the linear regression. For linear regression, the output is a continuous number. And you're going to find a mapping, a function between your input that could be one single feature or multiple features. So we have simple linear regression, which is one-dimensional feature and an output. And we have multiple linear regression. In multiple linear regression, you have several features that could be independent. There might be some dependencies between these features, and a single scalar value output. Okay, so, and we know the form of the function. That's going to be a linear function with some coefficient, one coefficient for each feature. These are called a slope of the line. The vector will form the slope of the line. And also we might have an intercept. Okay, so, and I didn't include all the description of the general description of the linear regression, because I assume you all know that because of the lecture in the course. Okay, so here I try to generate a very simple data set. In the beginning, I would need NumPy, matplotlib, because I'm going to plot some line, which is a plot. And also I'm importing inverse because I need inverse of a matrix later on. So here, I'm just generating some random number, 10 random number with NumPy, and I sort them. So this is how I form X. Here, simply I'm generating my function. This is my true function. In machine learning, it's called ground truth. So we know the ground truth. My slope is 2 and the intercepts is 3. So basically, I'm forming the function that I'm going to learn from the data. So it is all because I'm going to compare what is my fit, what would be my fit, and what is my real data. Here, so this is my ground truth. In order to have the real...
So sorry to interrupt. How do we get the ground truth?
I just define it.
We just define like a random...
it because I'm going to find this line.
Okay.
I have some data, and this is my fit. So I'm going to define the fit from scratch, and then train the model to see the trained model is exactly the same as this. So if I'm close enough to 2 and 3 as my slope and intercepts, I'm good. I'm doing good.
Okay.
So because I know this beforehand. Okay. And could you please explain again? I don't understand. You didn't understand which part?
No, the part I didn't got was
Oh no,
like, where do
I'm
you get?
asking one of your friends because it's not
Okay,
really. I
sure.
have a question in chat that is asking me to describe one more time, but I'm not sure which part. Durmesh is the name. Oh, okay. Linear algebra, which is LinAlg, is a package from NumPy, and it's going to make some mathematical manipulation easier, like inverse of a matrix, like root. And there are some other mass function from this library, but from all of them, I'm just importing inverse. It's not a name. See, here it's a name because I'm importing something and I'm calling it PLT as a name. But here, from this library, I'm just importing inverse because later on, I would need my inverse. Okay? We will see the impact later. Okay, great. So I generated my ground truth. I know what is the exact fit. And I'm going to train my model to see what is the trained model. In this way, I could just compare these two lines. Another step is to generate my real number. So in each linear regression, or even I can say most of the learning task, there is one estimated value and there is one real value. And you are going to estimate as close as possible. So y hat is my estimation. It's going to be my estimation. And y is my real number. So I know the estimation beforehand. And I'm trying to add some error to that to make some real number, because the real numbers are gonna have some perturbations. This is a random number, very small random number. I'm adding that to the values on the line to make some perturbation. Otherwise, if I do not add anything, I would end up with equal values. Great. So this is the real values, which is the blue dots here. And the line is the real value. I'm sorry, the estimated value. And now I'm going to estimate that again by training the model. I have the plot here. So we have reviewed this before. Whenever we are going to plot a line, we use plot. And I'm using the plot for drawing the line. And I'm using a scatter plot for drawing the dots, as I told you. And this is the input. Right? So here, I just want to define what is the number of x that I have. Let me show you x. X is an array, is a NumPy array, and it's a vector. So you remember I generated 10 random numbers, okay? And I would like to store this number in n. So what is n? Is 10. And what I'm doing in this line is to add a vector of 1 to my x. Does anyone know why I'm doing this? Why I need a column of 1?
This is because of the intercept?
Exactly. I'm in this example, I'm going to I'm not going to use scikit-learn. I'm just trying to find the vector, the coefficient vector by myself. So I need to train it line by line. I need to generate the algorithm all by myself, okay? So in my weights, I told you there is one weight for each feature and there is one intercept. In order to define the intercept, I need to add a column of 1. It's just a simple trick. So if I multiply x to the vector of weights, when I multiply the first column of 1 to like b, which is my intercept, it's going to be 1 scalar, and it's going to give me the intercept. Okay, so by this, and column stack is a method from NumPy. I'm adding a vector of 1 with size 10. I'm just stacking a column of 1 to the x. So see what happened. X now has a shape of 2 columns and 10 rows. So basically, I have 10 data points. A column is related to my initial feature, and the other one is for the intercept. We know how we could get the closed form solution from maximum likelihood estimation. And the closed form solution, which is called OLS, has the formula like this. You need to multiply x transpose by x, and they then take the inverse, again multiply by x transpose, multiply by y, which is the output, okay? And these are the real value output. Simply by doing this, I'm gonna end up with my estimated weights. And you see, I used inverse of the matrix here. I need to take the inverse, okay? And
Can I ask a question? I'm so sorry. Why for multiplying the matrices you use the at instead of the asterisk?
both works. I need just, yes, I need just, by asterisk, you mean this?
Yeah,
It's not gonna work for a matrix multiplication.
okay.
It is only for a scalar multiplication. But for
Okay, so
matrix multiplication, I need to use this. But I could
okay.
also use dot
Dot,
on
okay,
NumPy, okay?
okay, thank you.
That's nothing. So here, I'm doing a matrix multiplication. And when you do that, this is going to give me a vector which has the same dimension of my features plus an intercept. So here I'm expecting 2 values like this. And if you see, what was my grand truth? My grand truth is here. I had the slope of 2, very close to 2, and I have intercept of 3, again very close. So I come up with a train model, which is apparently a good fit. Why I'm just stating that it's a good fit? Because I knew the ground truth. Otherwise, I need to use some matrix to show me that would be a good fit, right? This is why I generated the ground truth, to simply compare them. Okay. That's nothing. Okay. Instead of using this matrix multiplication, you could simply use NumPy, linear algebra library, and from that you could use this method. They are completely the same. Okay, so you pass x, your feature, the output. I don't remember what is this parameter do, but I can just afterward check and tell you. And I'm gonna end up with the same W. So these two basically do the same. Now that we know what is exactly going on behind a simple linear regression, I would like to make it more beautiful and create a linear regression class. This is exactly what scikit-learn class do, with some differences. And the most difference is all about the parameters that we are not going to touch, but the whole framework is exactly the same. So what are we going to do here? I don't know how familiar you are with the concept of class and objects and method, but I'm just going to very shortly describe them. So by this, I'm defining a class. A class is giving me the option of generating a lot of similar objects with the same properties. So whenever I'm generating a class, I need to call the class first, and by calling it, I'm initially creating an object from that class. And all the objects from that class could have the same features and could have the same structures, it's better to say. So my class is linear regression. By having the init Thunder method, I'm defining an object. In this object, by just this line, when I call the class, the init function is called and the object is generated. Here I have add bias. It's totally up to me. If I'm going to consider an intercept, I need to pass add bias parameter as true. Otherwise, it's going to be false. In any fitting model, in any like learning task, we have the same structure, the same general structure. We need a fit function and a predict function. So there's a class, an object from the class is generated, and then I could call a fit method on that object. In the fit method, I'm passing my train set and also my train output, the output from my train set. And in the predict, definitely I'm going to predict on the test set. So by calling fit function, fit method, I would have the trained model, and the predict method helped me to use the trained model to have the output for the unseen data, for the new data set, which is the test data. Okay, so what's going on in my fit? In fit, I'm passing two parameters. If you don't know the concept of self, I'm not explaining it here. Just ignore it because it's a little bit more complicated to explain here. So we have X, the input is my train set, both X and Y. Here I'm asking if number of dimension of X is equal to 1, just add another dimension. Why I'm doing that? Because of the like this loop thing that I told you, because I'm going to stack more columns to that. So I need an extra dimension. I'm defining the number of data I have because again, I'm going to generate a column with the same number of data. Here, I'm putting a condition. If add bias is passed through, you need to go and apply this line. What is this line? As again, just like what we did before, I'm adding bias. Okay, bias is the intercept by just stacking a column of 1 to the initial matrix. It could have more than one feature. There's exactly the same, only the dimension would be different. Now I'm defining W, and for those of you that knows the concept of the class, I'm defining W like a feature for my object, and my object is self. So the W for my object, which is like the model that I'm going to generate from linear regression, is going to calculate it like this. Exactly the same that we did line by line. Alternatively, you could do this, I told you. And what is returned from this method is my object. This is why you saw it probably in the scikit-learn. This is why you call model the class, then you call the method function on top of the class, and then you call the predict on top of it. Predict is a method and could be applied on an object. So the output of this is the object, and you're calling a method on top of it. Okay, so moving on with predict. What's predict doing? Predict is basically receiving as an input my test set. Is checking if I'm still having a bias or not. If there is a bias and I'm required to have a bias, again, I need to stack a column of 1. And then it's just calculating the function, the predicted function, or the trained model. What was the trained model? What I trained is W. I have W, the vectors, the vector of weights. I need to multiply to my features, which is X. What is X? X is my input here. And then I would have Y hat, which is my estimate for the new data set, and return by H, right? So this is all done. All that is done by scikit-learn. You could simply define everything line by line. Okay, now I'm going to use that. First, I call the class. When I call the class, the init function is called and the object is created. Okay. What are the parameters of my objects? The first parameter, which is defined in the first place by calling the init function, is add bias, right? The object is created here, and then I have the object. I call fit. So I could do this, like, for example, I could do this in a separate line, and then again, do this. So they're basically the same, right? Okay, so I call fit by this until here. I'm going to have my train W. I call predict, and I'm going to have my estimated values, my predicted values, predicted output. So in fit, the input would be the train set, and for the predict would be the test set. Okay, but here I'm going to predict on the train set. Okay, there's no test set here, and plot the line. Okay, what I changed here? Let me see if the problem is from bias. This might fit a line, but I'm not sure what is this line. Oh, I see. I see what happened. Let's do this again. Because I run it multiple times and I'm just adding and adding columns. This is what it is. Okay, perfect. So now let's try on a different test data set. I'm again generating random numbers, 10 random number, and then again adding some permutation to the function. So this is going to be my ground truths, and calling linear regression again, feeding the function and predicting. The same happened. So it's only a different data set. The procedure is exactly the same. I'm just showing you because I wanted to show you that it's possible to have like something like this, you know, I just wanted to show you that I think it's toy data and the data is not that scattered. You could do this like with any classification algorithm as well, but that could be the best fit from linear regression. Great. Here I'm going to show you an example to try polynomial curve fitting with a very simple data set. My X is like 4 data, 2 columns of feature, very simple. And this is the output. So if I train the model and have my estimated W, it's going to be the fitted features weight, right? I'm going to do a polynomial curve fitting. And what is happening here? I'm going to project the feature into another dimension. So you know what happened in polynomial curve fitting or in any nonlinear regression fitting. So you have one feature and you are interested to make it more complicated. So in order to not fit a linear function, you're going to fit a nonlinear one, like a sigmoid function, like an exponential function, or like a polynomial curve fitting. And the technique is to just project your one feature into, for example, 10 other feature. And how is 10 other feature generated is by putting the initial feature into a basis function. And the output would be itself another feature. So I could have, for example, 10 sigmoid function, 10 different sigmoid function, and convert my one-dimensional or two-dimensional feature to the other 10-dimensional to the other 10-dimensional function. So by this, I would end up with 12 number of features. And what I have as a result is a fit and a combination of sigmoid function. It is going to be a very complex nonlinear fit. Here, for example, I'm going to do that on polynomial. Polynomial features I have, so this is the first vector is only for the intercept. The second vector is my initial feature. What I'm doing is projecting my first vector, I mean my first feature, to another dimension, which is 1, 4, 9, and 16. So I'm making all of this to the power of 2. So by doing this, I end up 3 features instead of 2 initial features. Okay. Now I'm doing the same procedure over and over again. So I end up with 3 weights. The first is for the intercept, my first vector of 1. The second is for the initial vector, initial feature that I have. And the second is for the power of 2 feature. Okay, I'm doing it again, and I would like to calculate the estimation error for the train. The estimation error for the initial data set is this. And now that I calculated it for the projected data set, I have this error. Now I'm going to increase even one more dimension. So which could be x to the power of 3, right? Because that's the polynomial. And these, after training, these are my new weights. If I calculate my error, it's going to be way less. So I am having less training error, but indeed my model is more complicated. Okay, so how I calculate the error, I'm just doing SSE, sum of a squared error. It is my estimated value. It is my true value. I'm calculating the difference to the power of 2. So this is sum of squared error, right? And the sum of squared error decreased significantly when I'm adding level of polynomial, right? Great. There is something going on here. If I increase this complexity, increase it, for example, rather than 3 level, I go beyond to like 10 level, I most probably end up overfitting because my model is going to be complicated. And when it's very complex, the training error is dropping significantly. But on the other hand, there could be a lot of test error, and there could be weak generalization. By generalization, I mean the power of my trained model on the test set or on the unseen data. Okay, so if I like increase this level, I'm going to be very close to 0. This is what's happening here. This is a pretty small number, and it's very close to 0, right? Okay. This is when we need regularization. And you learned what is the regularization, and I saw you have learned 2 methods, ridge regularization and lasso regularization. You know that ridge regularization is adding a penalty theorem to the trained model, to the loss function. And as the penalty term is convex, it's pretty easy to take the derivative and has a closed form solution. And the closed form solution is exactly the same. You only need to add lambda I, which is the penalty term multiplied by a matrix of 1s, right? So as it's very easier than lasso. So if you're going to train lasso, the derivative it's not that the function of the lasso is not, you couldn't have the derivative this simple. You need to define some sub-thresholding function, and it's not going to be this trivial. So I didn't include it here. Whenever you're going to use lasso, please just use libraries. But if you're interested to do that, I could even share the code with you. Okay, so here I define a regularization term of 1. So this is my feature. I have 4 vectors, 4 vector feature, because it was complicated enough, and I need to add regularization to avoid overfitting. This is why I'm doing this. Regularization is equal to 1. I train my weights like this, the same formula with an additional term. Okay, and this is my train W. So I'm eager to know what happens to the error it's a lot better right now. It's not big and it's not that much small. So it's showing me we have improvement. It's not overfitted anymore. Okay. Okay, now it's time to work on scikit-learn. So scikit-learn is basically doing all we did before, just it's pre-written and you could only use it and you're not involved with writing everything, all the estimation, formula, and closed form solutions. I told you there is an example on the internet, so I used that. The data set is on a GitHub. You could simply reach that. I'm going to show you the data set. The data set is related for an insurance company and the value that people pay for their insurance charge. And we are going to know how related are the features to the charge they are paying. For example, can we relate age to the charge, or maybe their sex to the charge, their BMI, the body mass index, and also whether they are a smoker or not, does it have an impact on the charge, and so on. So we have some categorical features that, for example, a smoker is a categorical feature, and it could map to 1, 0 because it only has 2 values. It's binary. Also, we have integer values, which is like children. Children cannot be float. There is a float BMI. Again, there is a binary feature, female and male. And also, I have another integer here. Another thing is that the region that they live, maybe this one has also an impact on the charts. Okay, but there's a problem here. Region is a categorical, but there is more than 2 classes for this, probably a lot of different regions. So we need to find a way to encode these categorical variables, right? Okay, so let's start with shape of the data set. So apparently we have like 1,000 and something data instances for different people, and as we explained, 7 columns. In order to have more information, I'm going to get info to see if I have null value and drop them. So there's no null value. I have the numbers, I have the data types. We talked about it. Okay, you remember we talked about correlation, which is Pearson correlation between each pair of variables. So it could be among all the features, and it could be among feature and the output. So this is a pairwise comparison. If you take a look at it, we are going to, what is important is the output, which is the value of the charts. And if we take a look at this column, so there's a relation between age. There's a relation between age and charts. You know that Pearson correlation is going to be between -1 and 1. Can someone explain what does it mean?
So if it's 1, it means that they have a positive correlation, meaning that if one goes up, the other goes up as well. If it's -1, it's a negative. So if one goes up, the other one goes down.
Exactly. So it's a negative complete relation, complete linear relation. And if we see something like 0.8, 0.9, we are so sure that there is a linear relationship between these two. But here, the biggest number we are experiencing is this. It's not that much informative, but we can rely on different things. And also, it could tell us that there is a linear relationship between age and charts, but it's not enough to state that. Why? Because sometimes the interaction of all the features include the results. I mean, there is a lot of interaction between all the features that you need to look at them simultaneously all together. So relation between one single feature and the output may not be enough. And also, as we see here, there is very important category here, which is smokers and non-smokers. So it might have an impact. Okay. In order to visually see this relation, we could use pairwise plots in Seaborn, which are so beautiful. So there is a pair plot in Seaborn that is going to give a relation chart between each pair of features. And as there are a few number of features here, we could do this to visually see if there is a relationship between these variables. For example, from this, like this, I could say, yes, there is something, but it's clear that there is some clustering happening here. So it's maybe a good idea to see if these numbers form 3 different clusters or not, okay? Or maybe here, what is this? Age and charge. So there could be a negative relationship between age and charge. So when people are getting older, they're going to pay less. Probably.
So sorry, but it's in the same, it is in the same graph because one is charge against age and the other is age against charge.
Yes, the same graph.
Okay.
Because it's pairwise.
Yeah.
Just basically changing the axis. Okay. And what else? So if you look at this number of children and charge, there's no relation between how much you pay for your insurance and number of children you have. And there is also something that is not evident from this charge, but it just popped into my mind. Sometimes the correlation between features inside features is also important. Because normally you don't want features that are too linearly dependent. If some of the features are too linearly dependent, there's no aim in including all of them in your training model. Basically, they're telling the same story, so they are not informative. So before in your pre-processing step, you need to pay attention to this. If some of the features are closely related to each other, there's no need to keep everything in your training model. Okay. Other kind of analysis that we could do, I told you, as you're seeing some classification here, and we have categories. We have categories in our database, so it might be an idea to pass hue parameter here. You remember hue from histogram we looked at together. So if I put here, I'm basically telling that I need smokers and non-smokers to be separate, to be 2 clusters. And the pairwise chart is here. So it's better now. Like charge and BMI, there is an evident linear relationship between charge and BMI for the blue dots, which is smokers. Okay, so there is a relationship here. And here as well. It is the same here as well. See? So sometimes just the correlation is not enough to see the relationship between, and the best way is, if it's possible, to have a visualization of that. And like this, it's only 2-dimensional. It's better to do that. Okay. Rel plot from Seaborn is also doing the same thing. So I'm just plotting it for age, for only one feature, age and charge. It's basically the similar thing. And also I'm passing the hue to see what is the difference between a smokers and non-smoker. And there's a clear linear relationship here, okay? So we can do that. We can just focus on one category for now. So what I'm doing is filtering all my data instances for the people who are non-smoker. And we worked with this in Pandas section. We learned how to put condition and how to filter row-wise based on a condition. So we define a condition and we filter the data frame based on this condition. And I copy all of them in a non-smoker new data sets, okay? So this is my new data frame, only for non-smokers. I still have the same features. Okay, now it's time to employ scikit-learn linear regression. Just like before, first of all, I need to import the linear regression class from scikit-learn and then call the class to generate the object. So model is an object from linear regression class from scikit-learn, right? Great. Let's do this. Now that I'm going to fit, I'm trying to only fit on the feature that I saw before a relationship. For example, age and charts. So how to choose only 2 columns is like this, because these are data frames. You are calling by the name of the column, like the keys of a dictionary. So I have X, which is my feature, age, and I have Y, which is my output, charts. This simple. Okay. There is one thing here. In my class, we just defined X to be anything. The only condition was that if it has only 1 dimension, add another column of 0, another column of 1 for the intercept. And there's no other condition. But for scikit-learn, there is a difference. You need to pass a 2-dimensional data. If it's a data frame, so you need index. Okay, so if it's a NumPy array, it could be NumPy array, it could be data frame. If it's a NumPy array, it has to have 2 dimensions, and it's a must. So if you have only 1 vector of features, you need to reshape it to have 2 dimensions, okay? But for a data frame, as my X is a data frame, it's already 2-dimensional because I have index, right? I have a column of indexes and a column of my feature. So it's 2-dimensional and we are all set, right? I just put help of the fit method for you to see there's a requirement for X here. So when I told you before, whenever there is an error or maybe you're not sure about the input, just please use the help function. So it is telling that you need to have number of samples and number of features. So it's 2-dimensional. Okay. The first thing that I need to do is to split my data set into test and train set. Here, I don't know why the other is doing that, but the train size is 30%. Okay, I'm not comfortable with the size, but that's gonna be all right. Okay, so by this train test split package, I could split xtrain, xtest to 2 parts, 30% train and 70% test. And I'm doing the same for the output, which is the Y, which is charge column. Okay. There is a shuffle parameter. It's always better to shuffle because you don't want, for example, maybe in your data, like the smoker are placed in the first rows and the non-smoker in the following. So it's not good at all. If you don't shuffle it, there are gonna be false information. So you need to shuffle at first. And the other input is X and Y in the order. So if I do that, I'm all set for fitting my model. I have generated the object. I'm calling the method on train set, which is X and Y, right? So now my model is ready. It's trained. In order to see if that's a good fit or not, I need to use some metrics. There are multiple metrics to compare how the trained model are performing. Two of them here is mean squared error and R2 square. Mean squared error, you knew it. It's like sum of a squared error and then taking an average. So it's average of sum of a square. And R2 square is another metric that it's a statistical metric. And for this, the higher is better. Okay, for R2 square. The error is just error. It could be any number, but R2 cannot be greater than 1. And closer to 1 is better, right? So I'm importing these two metrics. In order to have the metrics, I would like to do that for the test set. So I'm gonna measure the test error, not the train error. Both of these errors are important, always important. And you need to monitor all of them together. You need to monitor test error, validation error, and train error all together. But for now, I'm just doing it over the test set. So what is needed is to have the prediction over the test set. So I call predict on top of my object, which is the model. I pass the test as the input. Now I have the predictions. And what are the predictions? Predictions are the final output value coming from the fitted weights and the fitted function, right? Okay. To calculate R2 square, I need Y test, which is the true value of the test set. And I need Y hat, which is the prediction. I earlier called this Y hat, if you remember. And now I could come up with this R2 score. And mean square error as well. No difference. There is only an interesting thing here. I told you this is mean squared error. So this is sum of a squared error and then the average. So it's still on the scale of power of 2. So you could take the root from that. Okay. I saw some people just put SQRT to get the root, but there's no need to do that. If you want the root directly, you could just pass this through. Okay. And it's going to give you the root. And here. So this is my error, and this is my R2. Basically, I don't have the error from the other fit to compare. So I couldn't say anything from this number. I don't have any other test error, but I know that R2 is going to be less than 1 and as much close as possible to 1. So it's telling me that that's not a good fit. So by far, we have the conclusion that there's not a good linear relationship between charge and age. There's, and particularly for non-smoker, there's not that much relationship. So what we're going to do, maybe, as I told you, because of the interaction between the whole set of variables, and the output, maybe it's better to include more variable in our linear regression. Not only fit a line between only two set of like variables, one independent and one dependent. Maybe it's better to consider more than one feature. So I'm going to include age and BMI as well. So if I'm doing this, I don't have one feature anymore. It's two features. So it's going to be a multivariate or a multiple linear regression. Okay. Everything is exactly the same, but the only important thing is to like create new data set, because I have more features here, which is age and BMI, and then I need to display the data again. Shuffle is true, 30% train and 70% test. I call the linear regression. See, even the class is the same, because we saw before what is happening is calculating an OLS closed form solution. And for multiple linear regression and simple linear regression, it is exactly the same, right? We need to fit function on the train set and then predict the new data, which is the test set. Calculate R-score, calculate MSE, and then compare them. When I do that, let's see what happened. 4704 is still a lot and almost the same, even worse. So I'm not making an improvement. So maybe it's better to include also another variable, which is very important. And we saw that there is an impact between smoker and non-smoker in two different categories. So we thought maybe it's better to separate this number and to see a relationship within each cluster. But another idea is to consider this a smoker as a feature, because we are observing that it's important. The only thing is that it's a categorical variable. It's a binary variable. There is only yes and no. And I need numbers for a regression. So how do we do that? We could use map function. With map function for data frames, you could just simply say, if it's yes, put 1. Otherwise, put 0. Do you have in mind another method to do that? Anyone have something similar? No? Remember the function method we talked in pandas? How to apply a function and generate a new column. You could simply define a very simple function, have one input. If the input is yes, return 1. And if the input is no, return 0. And then apply that function. So the method was applied, right? And this is basically doing the same. So I'm creating new variables, new data set, again, splitting them and training the model. Now, what is happening? It's way better R2 score. So in this case, R2 score is better. So that could be a better fit, but still there is a lot of error, even more than before. Does anyone have any idea that why that's happening? I'm just asking this question to see if people are listening. Don't be afraid of just answering, even it's not Correct. The first thing pop into your mind. Nothing?
No, I have no idea.
Okay. People are sleeping. It could be, not necessarily. Maybe if you increase the number of variables, your error increases. It's not a rule, you know? The problem is that if you remember from the plots, like here, just think of the concept of the error. What is the error here? The error is the distance between the estimated value and the real value. And you see data is all over the place, right? They're I don't know the exact English word for that. They're so scattered.
Mm-hmm.
So they're far away. And
yeah.
For this data set,
can you go down? I think I might have an idea.
I'm sorry.
Yes.
I didn't catch you.
No, it's fine. I have the thing here. Don't worry.
Yeah.
See?
So this is the reason. So the error.
Will it have something to do to the fact that what you're putting as yes, so it's 1, and it's the smokers are like the ones that are farther away? So
you're telling it's because of the encoding?
Yeah, I think it might be of the encoding.
It might be, but the major reason is that the structure of the data is like that. It's not concentrated. It's very scattered all over the place. So there are huge amounts of errors. Even if you come up with the best possible fit, you could
because what we were doing earlier was just with the non-smokers, right?
Mm-hmm. Right. Yeah. Exactly.
So the non-smokers are like more clustered,
more concentrated. Right.
Exactly. So when you add the smokers, it creates more.
Exactly. So I include all of the points, and the points are just very far away. So despite the fact that I'm generating the best fit, this is the best fit possible, but it is still showing a lot of error. Okay.
Maybe is it possible we can remove some of the outliers, with the condition?
Exactly. Yeah. Outlier that has an impact on this, has a huge impact on this, right? But all in all, we care about the best fit. And the fit is somehow satisfying here, right? Okay. And when you end up with this, you could think of different ways to fit your model. Maybe you're not using the correct method. Maybe it's better to include some classification first and then do the regression. Okay, it's because you haven't explored the structure of your data correctly. Okay, moving on. If you train your model with you saw in my model, I had in my class there was self.w. So simply if I call the object and then w attributes, I would have the vector weights, right? But here in scikit-learn, it's actually the same. They have coefficient and intercept feature for this object, right? So I could call them, and I have all the features, all the feature weight, and the intercept as well. So this is how you call them, and you see them. Okay. Now it's time to predict the value, predict the output, the charge for a new data set, for a new unseen data set. So how? Simply by making the function, the linear function we trained. I'm defining a function here. The inputs are my variables, are my features. I would have age, BMI, and a smoker variable for a single new data set. So coefficient 0 is related to age, multiplying by age. So C in manual, right? I'm pronouncing correctly?
Yes, and manual. Yes.
In manual, great.
Yeah.
You see, this is asterisk here because it's a scalar. It's not a matrix anymore, right? I could use a scalar, but because I could use a matrix because I'm putting single value feature, I cannot do that. So plus BMI to the first coefficient and a smoker multiplying by the third one and adding the intercept. So this is how I calculate the charge for a totally new data. A person with age 33, with BMI 22, and he's not a smoker. Great. So I could have estimate, and this is the whole point behind doing a linear regression, because you're going to predict something for a new data set. As the website, the original tutorial suggests, we could do different things here. We could add like all of the features to see what would be the impact. We could, for example, here's the original data set here. We could consider like sex here as another binary variable by mapping it again. You could just map female to 0, male to 1, and do the same step again. Another thing is about the region. I mentioned that region is a categorical variable. What you could do is to find an encoding for this. How to do this encoding? Does anyone have any idea how to encode categorical variables? No? There's a method called one-hot encoding. One-hot encoding. One-hot encoding is for encoding categorical variable. And how is it doing things? It's basically like this. Just equal to the number of unique values you have. For example, you have 3 region, for example, A, B, C. You have 3 region, and you have 1K data. Okay, so you need to generate columns with the same size, but 3 columns. Okay, column first is column A, column second is column B, and column third is column C. At any time, for any data instance, only one column has value of 1. So if you sum over all the columns, that's going to be always 1, not more and not 0. So it means that any person is assigned to one region. Okay, so this is called one-hot encoding. So you're adding a lot of new columns just equal to the unique value of your categorical features. Okay, and by this, you're changing the categorical variable to a numerical variable, and you can do the linear regression by this.
Couldn't we add, like, for instance, southwest, the number is 0, then northwest is number 1?
Exactly, you need to do that. You can do that, but the thing that you're mentioning is only the title of the column. The title of the column is not helping you.
But could we do like just one column with like 0, 1, and 2? and then just assigning those numbers, those values,
No,
or
no, you can't, because they have different scales. They have two is greater than 1, and there is no superiority for like another region. By this,
okay,
you're creating a relationship.
okay.
It's not correct. This is why people do one-hot encoding. 1,
Got it.
0. Yes, they're changing it to 3 different binary feature.
Because the model could interpret, could think that 2 is higher than
Exactly.
0.
2 is higher than 1. 3 is higher than 1. So there's gonna be a false relationship between variable.
Got it.
So but you need to pay attention that these one-hot encoded columns are related. They are a group. They are not independent. So whenever you consider them, I'm telling this because you need to pay attention. You need to consider all these 3 columns simultaneously in your training process. You're not allowed to consider, for example, one of them. They're interdependent, right? Okay, so you could do something like this. One-hot encoded the region, or map the sex column and see how the result change. So I try to move on. If we have extra time at the end, I will just give you time to do that on your own. Data pre-processing always work. If you have outlier, and for example, and if you have in training task like this, that outlier that have an impact on the output, it's always good to do the pre-processing. But for example, if you have another learning task like support vector machines. Support vector machines is they're not sensible to outliers, right? Or even decision trees. So it all depending on your task. But basically doing pre-processing always help. And it's a very important initial step before doing any learning task. Okay. Okay, up to here. Now, moving on with logistic regression. So logistic regression is a very important learning task that is designed for binary outcome. If you have 0, 1, if you have yes, no, true, false, so any binary outcome that you could like you could classify the data into 2 points based on the output, that's going to be a logistic regression task. And you can look at it as a classification method as well, because it's classifying your data into 2 sets. For example, you have a lot of features from information of a patient, and there's a lot of like blood factors, and with analyzing these blood factors, you could understand the probability of a person surviving or not from a disease, for example, or if there is even I cannot enumerate. There's a lot of application for logistic regression and multi-class regression. I'm not sure if you cover in the class multinomial or multi-class regression.
No, we stopped at logistic regression.
Logistic regression. Okay, so it's going to be for the next tutorial. So even multi-class logistic regression, for example, if you have there's a very common practice for that, which is this discovering handwritten digits. We have 9 digits and there's a lot of handwritten text. So the task is to identify which one is 1, which image is 2. So it's classification, but it's classified in more than 2 classes. But for logistic regression, is a binary classification method. Okay. I'm here I'm using a Titanic dataset. Titanic dataset is a data showing based on some feature, showing the probability of people survive from Titanic event or not. So I have included the CSV in the model. I need to import scikit-learn, pandas, and a good method from scikit-learn, which is a standard scaler. A standard scaler is doing a standardization. For many tasks, including regression, it's better to standardize your data first, because not only it's simpler, easier, but also it helps to reduce the negative impact of the scale and the magnitude of your data. Sometimes if you don't do the standardization, for example, in many classification algorithms like KNN, if you do not do standardization, it's gonna end up with awful results, because features, all of them are in different scales. Some of them are too small, some of them are too big, and it's gonna fit a really bad model. So you first need to standardize your data, and it's always better to do that than not doing that. So I'm reading Titanic data, but let's first see the data. So this is a data frame. I have some features here. This is the fare of their ticket. This is the class of the ticket. The lower, the better. So the lower class is more expensive. So these two, like the class of the ticket and the price of the ticket, has a evident linear relation. And this is what I mentioned earlier. When you have two features that are linearly dependent and there is an evident relationship between them, there is no need to consider all of them. So it's clear that you buy a better class, a high-end ticket, it's gonna be more expensive. So there's no aim in including both of them in your model, but for just because there's only like 6 or 7 features, so we could do that. But when you are facing, I don't know, like more than 1K feature, you need to choose the most important features. So what is important for us is the survive column. Survive is the output of the model, the thing that you're going to predict. You're going to see that people with different characteristics survive or not. Their age, I don't remember what was this, what these two was. I don't remember, honestly. Okay. So first of all, I need to store all my data in X. And do you know what is this? What I'm doing that? No? What is that value is doing? No idea?
I might have a clue. Does it have to? I've seen that. I think it has to do with something that instead of having like the
Number of
key,
dimensions.
yeah, I don't know if it has something to do with the key and the value that you want specifically the value.
It's not that.
Okay.
I just like to work with NumPy array.
Okay.
So
Okay.
that values is changing my data frame to NumPy.
Okay.
So the type of this is NumPy. I just wanted to show you when you convert between data frame and NumPy. Nothing different. So here I have a different, and I am using drop method from Pandas to drop the column of survive. So basically I'm asking to drop all the values on the column x is equal to 1 because it's my result and I don't want to include it in my feature, right? It's the outcome. It's the target. And here I have my target vector. Again, I'm changing it to NumPy. And specifically, I'm just calling survive. It's not drop. I'm just calling the column survive. Okay. Something's happening here. I just like to do that. There's no specific reason for that. Yeah. I could continue with the pandas. And I can say you the reason because I in the past I generated the class and my class was written in some way that needed NumPy. And for the case of your tutorial, I just omit my class and continue with logistic regression from scikit-learn. This is why. But for scikit-learn, you could input data frame. Okay. Something's happening here, which in my opinion is very important. First, I split the data. I generate my test and train, and then I call standard scaler and standardize my data. It's very important. You need to first split and then standardize. Do not ever do that. First, standardize the data over the whole data set and then split them. Okay? Because if you know reason. Because if you do that, what is standardizing doing? It's subtracting all the numbers from a mean and dividing them to the standard deviation. If you split them, you consider the test data as an unseen data. You're assuming that you do not have the test data. You're training the data, your model only on the train set, right? And if you first split, it makes sense. You have two categories, and then you calculate the mean for each of the like each of the subset, right? But if you do not do that, there is a mean which is not valid for the test data, and you're mixing everything. So always remember first a split and then a standardize. And a standardize is very like easy. You just call a standard scaler, fit on the train and transfer. This is the syntax, right? Okay, xtrain and xtest, if you call them, they're all standardized. It means that they have average of mean of 0 and a standard deviation of 1. So they're going to be between -1 and 1. Always check your result. So I'm calling a logistic regression from scikit-learn. And here I'm using, I told you, there is a lot of metrics to compare the functionality of your model. Here I'm calling ROC, and area under it, the area under ROC curve. I'm not sure if you know ROC. Are you familiar with this concept? No? I can just in short say that that's a matrix to like compare different models based on TPR and FPR, number of false predicted values and number of true predicted values. So these are the things that are very important. Importantly, show if you are predicting positive, you are predicting it right or wrong. So true positive, false positive, these are values that's very important and makes this matrix. So ROC is a curve, and AUROC, or area under ROC, is the area under this curve. The higher, the better. So I will show you the shape of the curve later. So now, again, it just have exactly the same step as logistic regression, as linear regression, or as like any other training models. You first call the class, you create the object, you call the fit, and then you call the predict. Okay, so fitting on the X train and Y train. Here, I'm just making it as a separate object. So I'm storing my object. And then again, I'm calling predict on the top of my object. Here I have predict prob, which is predict probability. You know, a logistic regression is giving me probability of being 1 or probability of being 0. And it's one of the good things of this model because it's always better to have probability. And if you define a threshold, like for example, you consider a threshold of 50%. If your probability is higher than 50%, so they're going to survive, for example. And if it's less, it's going to be otherwise. So it makes you able to put a threshold. For example, you're going to put a higher threshold. If the output is going to be higher than 80%, they're going to survive. So it's all on you. So, and we mostly probability is more desired than a single value prediction. Okay. So I'm having probability for the test set. Okay. And I'm storing it in a vector of probabilities. By these two lines, I'm calculating false prediction, true false positive predictions, and true positive predictions to be able to plot the ROC curve and also the area under the curve. Okay, so these are two metrics here. If you don't know the concept, just do not forget it because it's important, but just you need to see the result afterward. Another thing that I can realize the efficiency of my model is accuracy. For classification, you can calculate the accuracy. How? By checking the value, because it's classification, it's categorical. At the end, your prediction would be a set of 0 and 1s as your prediction. So you need to compare the true predictions and calculate the number of true predictions. If predicted value is equal to the real value, that's going to be 1, and you're going to sum all of these ones together and divide by the whole number of the set. So by doing this, you're going to come up with the training accuracy and test accuracy. Okay, and both of them are important. So I'm feeding the data, feeding the model, and I'm sorry, predicting the model on train, because I'm going to calculate train accuracy, and also I'm predicting the test. I am storing them in the like prediction. So these two are different. It's giving me probability and it's giving me the prediction value, right? And now I can use the the threshold I told you here. If the prediction is greater than like my threshold is 50%, is greater, I'm changing the result to integer. And so what is the output of this? The output is a Boolean, is true and false. So true would be converted to 1 as an integer, and 0 would be converted to, false would be converted to 0 as an integer. So here I would have the exact 0, 1 value as the results. Now that I have them, I could compare it with the real value from train set and from the test set. And as I told you, I'm summing all the numbers that are equal. When they're equal, it means there is a true prediction. Both of them are 0. Both of them didn't survive, or both of them are 1. So it is survived for both values. Both values, I mean the predicted value and the real value. So I sum all of this. You know that the output of this is again true and false. And when you sum a lot of true and false, you're going to receive the number of correct ones, the total number of correct ones, the total number of true ones, and dividing by the length of your vector is giving you the accuracy, and I can print it. Okay, what I did wrong. Let's do this from scratch. Okay. So train accuracy is 78% and test accuracy is 83. And they're good numbers. It's a good accuracy for this model. Okay. So now I'm sure that I have a good fit, I'm ready to visually see my coefficients. So remember, it was a logistic regression, but still, it's correct that it's not a linear fit. It's a sigmoid fit, but still, I have a coefficient for each single feature. Okay. By coef feature, I could see my coefficient values and I store them in this array. So for each of them, I have a value. For example, it's a big value. It was for, what was the first? Okay, let's see it here. I store the name of the columns, the name of the feature here, and I can plot a bar plot. See? It's important to compare the impact of the features on the result, and it's telling that the highest impact is coming from their stacks. Okay, and it has a positive impact. So where is the data set? I don't know if sex one is male or female, how they encoded it. But for example, you could say if they are men, they survive more. If one is men. And the next biggest one is the class of the ticket, because it's probably because of the point that people with like business class are sitting in a safer place. Or maybe no, it has a negative impact. But I'm right. It has a negative impact, but P class is the lower the better. You get that? So if the lower, it was better. So it's the same fact. The better tickets, the better chance of survival. Okay. Okay, so it's these kinds of like plots help you to realize your model way better. And this is the RC curve I mentioned. See, this is a random chart. Okay, just a diagonal line, and this is my logistic regression curve. It is called ROC, and the area under curve is 0.9, which is a very high number. Closer to 1 is the best. So it's showing that this model has a great performance. For example, you could do the same analysis for different models. As it's a classification, you could do the same classification with KNN, with like decision tree, with support vector machine. They're all doing a binary classification for you. And then you could plot this ROC and compare these together, because no matter you fit the best model for each data set, a specific model works best. And you cannot say that which model works better. You need to try that to see which one is giving you the best like area under the curve, right? Great. Okay, so this is the last one, hopefully. And this is a logistic regression I did on the toy data. A data that is generated, sample data, which is randomly generated between 50 data between -5 and 5. And I'm also generating the output. For some of them is 1, and for some of them is 0, right? I'm like training logistic regression from scikit-learn. And you see here, do you know what is the reason I did that? I'm not continuing until you say, because I just told you the reason. Maybe I can consider a point for my questions here, a substitute to your quizzes. Nothing? What is this reshape doing here? Okay, let's see what is X. When I generate X, what is X? A set of random number between -5 and 5. It goes to the last end.
Is it doing the same as standardized?
No.
No, okay.
Nothing to do with a standardized. So I just have some number sorted from -5 to 5. So what is basically reshape doing? Okay, maybe it's better to do this. Let me do this. So I'm simply fitting a model from scikit-learn. We learned that we need the train sets into the fit and the test in the predict, right? It helps to consider the last n value. What do you mean last n value? I don't get you. If I also don't do the reshape, it's going to consider all of the 50 value. There is 50 value here. I didn't split anything. I don't have a test and train. I just have a train set. I'm going to fit the model on 50 random number between -5 and 5. And I'm generating y as the output. Okay. Okay. Let's make it separate here. Okay, and what is y? Y is a Boolean valued output for 50 number, and is sorted, as I told you. So because it's basically between I'm just classifying my number. So if it's greater than 0.5, which is here, it's gonna have output 1 as type int. So it's changing like the float to integer. This is why it's changing to 1, and otherwise 0. Okay, so everything's correct. Now I call logistic regression class, and then I'm fitting the model. Let's do that. Can you just read the error to see what's happening?
So it's basically converting a 1D to a 2-dimensional array,
Exactly.
reshape. So
Exactly.
when we give -1 and 1, it just creates a new column so that we
That's
can.
it.
Okay.
That's it. That's it. Because I told you, scikit-learn method is like needs a 2-dimensional input. So never pass a 1-dimensional input. And that's it. This is why I have an error. So it's asking me to reshape it. And if I reshape it, what is the shape? It's 50 to 1. So it's generating another dimension. Nothing's changed. It's just having another dimension. See, this is about x. It's a vector. And when I do the reshape, it's 2-dimensional. It's matrix. So I need to pass this to avoid the error. So sometimes you think you're doing everything correctly, but you're just not doing the right standard for that specific like method or class. And that's it. Okay, so it could perfectly fit my data. Great. Any questions so far?
Nope.
We're good.
Yeah, I had a question about the types of regression. For instance, you said we have to run n number of models in order to get the perfect fit. So that's the only way, or we should know like we have to perform all sorts of regression in order to get the final answer.
The question what was why we need
Yeah,
to apply more model?
yeah. When can we determine this is enough? For instance, I'm doing only two. When will I know the third model is the right fit? How can I be certain? And is there any way to check?
Okay, yes,
Yeah.
I understand. Okay, so first of all, consider all the metrics you have. For example, the RC is a very good metric, especially for the classification, binary classification and multinomial classification, more than 2 classes. So first, take a look at your metrics. If it's high enough, if it's good enough, you're good. Okay, but sometimes you need to be very good. You need to have even better solutions. So you need to think of other learning tasks that might be possible to apply on your data. For example, okay, that's a binary classification, and there's a lot of more classification method that apply for this. And the good point is that you have all the libraries, and they're not that difficult to apply them. You're not going to write everything from scratch. You have everything pre-written. So the thing is only applying them, just comparing them. Why? Because sometimes some of the model fits better to the structure of your data. We talked about like outliers. Some of the models do not care about outliers, and they do the best, even in the case of outlier existence. And for example, you forgot to do a good pre-processing and ignore all your outliers. So suddenly you apply like a model like decision tree, and you see, oh, there is a higher area under the curve. So you could understand, yes, that's learning.
So at the end of the day, it all depends upon the area under the curve. Or else is there any other factors? Like for instance, you said there was 0.9 closer to 1 for logistic regression. That was a best fit. Can I stop there, or should I aim for the 1? Is it possible to even get a 1? Is it like that, or
It's
no?
not possible to get 1.
Yeah.
It's not even good to get 1.
Oh, okay.
If you have 1, you're probably overfitting.
Okay.
You
So I'm
are
making the
too
data
good.
to I'm modifying the data in order to get the perfect value. That's not right. Yeah, okay.
Exactly. So when I reach IUC like 9.9 or maybe 0.94, it's great.
Okay.
But you need to consider a lot of things almost simultaneously. For example, you need to take care of overfitting. And how do you know overfitting? For overfitting, you need to plot. You need to fit the data, fit the model, and then plot your training, validation, and test error. Okay? Because as you move forward and as you make your model more complicated, and you have more iteration in your fit. What I'm saying, for example, in the logistic regression, I don't know if you know what is, I think you know what is happening behind the scene. It's all gradient descent algorithm. Okay, so for gradient descent, it's not a closed form solution for logistic regression, and even for multinomial regression, multi-class regression. It's gradient descent, and gradient descent is an algorithm, iterative algorithm. So it's not gonna stop until you ask it.
Okay.
But there is a limit on the number of iteration. What does it mean? The more number of iteration, you are getting closer and closer to the best fit.
Okay.
And okay, so as time goes, you are getting closer to the best fit. So your training error is dropping. So everything is going better. But there is some point that if you plot and if you monitor the validation error, you could see validation error suddenly increase, or test error suddenly increase.
Okay.
So this is the point that you need to stop.
Mhm.
Okay, so you're
I have to stop and go
there.
for the next. Okay.
Yeah, you get it?
Yeah.
Great. I have from my own code, I have some things there to show you. Now that if I can find it.
So when you said if you're not doing your pre-processing correctly, does the one hot encoding that you mentioned earlier, is it used to do data pre-processing, like to?
It's a data pre-processing step. Everything
Yeah. Okay.
everything you do before training your model is pre-processed.
It's okay. Got it.
Right? Okay,
Yeah.
let me show you this here. I didn't include these things because it's
Oh, now I
these-
see.
you haven't covered these like
Yeah, I get it. Yeah.
so far, but see, just for the sake of just taking a look. Here's a logistic regression that I wrote from scratch.
Yeah,
And
you define the function with the
define
framework.
class,
Yeah,
find
got
how to get like the gradient algorithm and so on. Okay,
Okay.
this is the k-neighbor classifier, KNN, which is
That's
a
a
method
yeah.
for classification, and this data is a binary classification, decision tree classifier, and logistic regression from scikit-learn. Okay, see, there is difference performance. For all of these four, this is the best possible fit.
Okay.
You cannot say the fit is wrong. The fit is okay. But comparing these four different methods, they have different performance. And best of them is logistic regression.
Okay.
Okay, so it's telling me that this specific data set needs logistic regression more than decision tree.
Yeah, got it.
Great.
Thank you.
That's nothing. So no more question? So I guess
Just I had one question. Why we are downloading the sub packages? We are let us say
because
NumPy.
I don't want to make everything over there. I mean, I just need some very specific thing from that package. So I didn't import all of them. I just wanted to be specific, but you could import all of them and put an alias on it, put a name on it, like what we do is with pandas, what we do with NumPy. We didn't import a specific method. You could do that. When you import, you could just simply import what you need or import all the package.
Yeah, so nothing different, right? Both are
No,
fine.
nothing different.
Yeah, okay. Thank you.
You're welcome. Great. It was very good to see you guys today. See you in the next lab. Have a good night.
Bye-bye.
Bye.
Thank you. Bye.